Hello students, I'm going to go over chapter 9, the first part of chapter 9, simple linear regression, as a little review. Going over the PowerPoint and going over a couple examples. This is simple linear regression, so it is the attempt to measure the association between one dependent variable y and one independent variable x. Remember that the dependent variable is the one that you are trying to predict, and you're using the independent variable x to make that prediction. So we're going to look at the following things: the correlation coefficient, Pearson R, simple linear regression, the coefficient of determination, the R-squared value, and then going through an hypothesis test process as well. So just as a recap, Pearson correlation coefficient R, value that measures how correlated two variables are. It will range from -1 to +1. The extreme values being that perfect correlation, either positive or negative. Generally, values around 0.7 indicate a strong correlation, so it could be strong positive or strong negative. Negative correlation just basically means that one variable increases while the other variable decreases, whereas a positive, both are moving in the same direction. Regression line. Similar to what you may have taken in high school math or other math classes, where you have y equals mx plus b. In stats, we rearrange those terms. So we have that y with that symbol, that means estimated y value, equals b0, which is the intercept, plus b1, the slope, times x. So that is our regression equation for simple linear regression. So we substitute in any value for x, multiply it by the slope, and add the value of the intercept to that, and we will get an estimated value for y. R-squared value is the coefficient of determination, measures how well the independent variable explains the dependent variable, usually expressed as a decimal or as a percent. So R-squared value is squaring Pearson correlation. So R-squared value will always be positive, and it will range from 0 to 1. So we're going to go over an example to show how we're going to find and interpret all these values. So this is a basic example. I'm not sure if it's on page 117. We're going to use Excel's regression tool to create that summary table. So this is data of 6 observations, Math 30 high school grade, with anticipated perhaps Y would be a grade in stats course in university. So a student who finishes with one student who finished with 86 completed or got 82 in the stats course and the Y course, and we have other observations. We're going to see if there's a correlation between the independent variable and the dependent variable, and if there is, we can actually develop and use the estimated regression equation. So that's going to be our process. We're going to come back, work on this example, because ultimately what we want to do is test to see if there is a significant relationship. We're going to use the slope to test to see if there's a significant relationship. So I'll come back to this slide after we run some of our numbers. So we have, I'm going to go into Excel here. We have the data. There's a data copied from the PowerPoint, the 6 observations. And what we do to kind of create the output is we go into the data tab and we use data analysis. So I'm just going to do a quick overview of how to find this data analysis tab, because it's generally not listed there, shown there, until we add it. So we have to go File, Options, Add-ins, click OK or click Go, and make sure this analysis tool pack is checked, and then we can click OK for that. And then it's going to show under the data tab, it's going to show the data analysis. So let's go into data analysis. We're going to go down to regression. It asks us to input all of the y variables. Do the same thing for the x. We have labels, make sure we check mark labels, and we're going to go into a new worksheet. And basically clicking OK we get all the values we need. I previously have it here. Need it a little neater. Let's get rid of that. So on this table, what do we need on this table to know? Well, a couple things. Let's shade this in yellow. This is Pearson, the Pearson's correlation. Oops, this is R. This is the coefficient of determination. Basically, this is R squared. So this tells us that there is a positive correlation, a strong positive correlation between Math 30 grade and the grade Y, the grade in a university stats course. This value tells us here, if we convert that to a percentage, tells us that there is a 75%, or that using the independent variable, math, it accounts for 75% of the variability or unknownness in the grade, in the stats grade in grade Y. Here we have the number of observations. We know that there's 6 pairs of observations. Right in here, we have our intercept and we have our slope. So this one here, I'm just going to type in here, slope. So from here we can develop that estimated, or we can develop that estimated regression equation. So y equals, capital y equals the intercept, negative 2.8857, plus the slope, x. So now we can substitute in any value of x to get what we would predict or estimate the grade y to be. Okay, so let's go back to our original question here. We have, where are we here? Okay, we have basically determined, let's go back here. Sorry, there it is. The correlation coefficient R, the simple linear regression equation, and the R squared value. Now we're going to look at the hypotheses approach to determine if there is a significant relationship, because if there is not a significant relationship, we do not want to use this estimated regression equation. We'll only use this equation if there's a significant relationship between the two variables. And that can be measured in linear regression, simple linear and multiple linear regression, by using this value right in here. This is a test statistic for F, which equals 12.024, and this is the p-value for F. So let's put those values in there. Let's just go like this, make it a little easier. Oops. And here. So remember, our decision rule in linear, simple linear regression will be to reject the null hypotheses if the test statistic is greater than the critical value. I'm just going to type that in there, critical value. Or we can make the same decision by looking at the p-value. Reject the null hypotheses if the p-value is less than alpha. Looking back at our question, doesn't specify alpha. Let's just assume that alpha is 5%. So we're going to run this hypothesis test using the alpha value, the level of significance at 5%. We are going to reject, use this decision rule to help us make a decision, to reject the null hypothesis if the p-value is less than alpha. The null hypothesis is that there is no relationship. So the slope of the population equals 0. We test to see if there is a relationship, if there is a value, the slope does equal something other than 0. In an f-test, we always take the values given to us. So we don't have to worry about if it's a one-tailed or two-tailed test. Let's go back here. There is our p-value for this. P-value is 0.02564, which is less than alpha. Let's just type that in there right there. Alpha is 5%. So basically our decision would be to reject the null hypotheses. We can also find the critical value of f. In order to find the critical value of f, we need to go to the f distribution chart, which is this chart, using alpha 5%. Degrees of freedom for simple linear regression is k, degrees of freedom in the numerator. K is the number of independent variables. We have one of them. So we're going to be using this row. And n minus k minus 1 for the degrees of freedom in the numerator. So we have 6 minus 1, which equals 4. The critical value is 7.71. So we can type that in here too. F, critical value, 7.71. Comparing the critical value to our test statistic using our decision rule, reject the null hypotheses if the test statistic 12.02 is greater than 7.71. So we make that same decision. We can also make the decision based on a t-step approach, because in simple linear regression there's only one independent variable. So there is our test statistic and our p-value. The p-value for the t-value and the p-value for the f process are going to be the same values. So these values here will be the same. Let's just make that a different color. For simple linear regression. So the decision rule is the same. Reject the null hypotheses if t is greater than the critical value of t. Or reject HO if p-value is less than alpha. Oops, can't type. Alpha is still 5%. We know the test statistic is 3.46. We need to find the critical value. Oops, can't type. Critical value of t. Using the t-distribution chart, we're testing at 5% level of significance. So we have n minus 2 degrees of freedom for the t-distribution test. And because it's a two-tailed test in essence for the t test process, we are going to be using 2.776 degrees of freedom for our critical value. .776. So comparing the test statistic 3.46 to 2.776, we are going to reject the null hypotheses. We can also look at the p-value. We can find, I know we can't find that p-value, but Excel can find this p-value. This p-value is already being doubled because it's a two-tailed test. So we can look at this value, 0.02564. It is less than alpha at 5%. So using the p-value approach, we are also going to reject the null hypotheses using the p-value approach. So the values we have in here, the p-value for the test statistic process has been doubled because it's a two-tailed test. We found the critical value using the 0.025 level or column, and we can compare that to our test statistic. So that is simple linear regression, the process of that.